All righty. Well, we get settled in. It is my pleasure to introduce our next speaker, Mike Prince. Mike Prince is the ARV project manager in the NSF Office of Polar Programs, and he will be speaking to us today about designing CI for the Antarctic Research Vessel. So please help me welcome Mike Prince.
Morning. I'm a fish out of water here. I'm a ship driver. I was responsible for data collection on my first research ship in 1980. We had a 12 kilohertz depth sounder and a line scan recorder, and the data was the piece of paper that came off the line scan recorder. One of my friends was a scientist, and he used to read a spreadsheet over the radio to his boss. So anyway, we've come a long ways. I'm part of a team. I'm a rotator from San Jose State Moss Landing Marine Labs. Part-time as the project manager for the ARV. Oh, I should have started my timer. The team is led by Stephanie Short, who's responsible for all the infrastructure and logistics in the Antarctic. She's a section head for what we call AIL. Tim McGovern, his day job is managing the current research vessels, Nathaniel B. Palmer and the Lawrence M. Gould and the Palmer Station. And he's the program manager for this. We have on detail from the PEO ships, Navy, Caitlin Jarecki. She actually was a program manager for the construction of the Neil Armstrong and the Sally Ride that are at Scripps and Woods Hole. So she has a lot of experience with building ships for the Navy and is including research ships. And I'm joined here today with Tim Howard, he's the AIL Information Technology Support Manager. He's responsible for cyber security within the U.S. Antarctic program. Next. So this is the ARV. This is the artist or the rendering from the designs. It's going to be an impressive ship. It is replacing the current icebreaking research vessel, the Nathaniel B. Palmer. It's going to be bigger, more scientists, 55 versus 45, a lot more lab space and deck space. Endurance is 90 days, which is a big design driver. The amount of fuel we need and the size of the ship is driven by that requirement, as well as the power necessary to break 4.5 feet of ice at 3 knots, which is a greater capability than what the current ship has. Allows us to get to pretty much anywhere around the Antarctic continent, and we hope year round. Those are key performance parameters: the ice breaking, the labs, the berthing, and the endurance. This is an eye chart. You can look at it at your leisure, but it kind of gives it, a summary of all the specifications of the vessel. It will be a U.S. Coast Guard letter. It'll be inspected by the Coast Guard as an oceanographic research ship and has various classifications from the American Bureau of Shipping to make sure that it meets all our requirements. And you can see many of the drawings and reports at the future.usap.gov website. Where we are in the process, the major facilities at NSF go through a design stage. We've successfully completed the conceptual design phase. We are essentially done with the preliminary design phase, and we have approval from the director to move to the final design. But before we do that, we need to hire a vessel integrator to carry the project through. And there will be a request for proposals from industry within weeks, I hope. Once we finish the final design phase, we get approval to move to construction stage and Congress appropriates the money, then we can start actually building the ship. The project is guided in a lot of ways in terms of what we're going to build by the research infrastructure guide, the rig, and we have a set of science mission requirements that have been turned into performance specifications that drive the design. The execution plan includes sections in systems engineering that includes a cyber IPT integrated product team. And then section 12 is dedicated to cyber infrastructure, cybersecurity. So those are our documents that we refer back to. The project team, the contractor that's been carrying us through the project so far, includes a very well-organized systems engineering team, and includes a very strong component that's dedicated to cyber infrastructure and to some extent at this stage, cybersecurity. The person that's been leading that effort on the contractor's part is really phenomenal at understanding the specifications and keeps everybody else in line. So our cyber infrastructure requirements, a lot of what you've been talking about is data management, and how you get data to the users. At this point, what we're concerned about is the sensors that create the data, the systems that create the data, and what the scientists are going to be using and what the ship needs in order to actually operate. So there's a lot of, within the cyber infrastructure, there's a lot of ship systems, power management, propulsion control, navigation, communications, the life support systems, automation and alarm systems. All of those networks, they're dedicated networks for all the sort of ship systems. And then science, of course, communications, data management, during the course of a cruise, there's, the scientists want access to the data they were generating, how it's displayed and how they archive it and what they do with it eventually. But we have a lot of acoustic sensors, met sensors, seawater sensors, ice and weather, remote access and outreach are all part of what we need to work on. And then, of course, there's 84 people on board, and they're bringing their iPads and iPhones, and they want to check their Facebook page, and that's kind of challenging when you're working in the polar environment. We think it's going to get better with Starlink and things like that in the future, but anyway, a lot of demands. The tops, this is, just sort of a picture of the top side arrangement. All those little dots and things are various sensors and antennas, all have to be connected into our network. One of the things that we've been spending a lot of time on is, satellite communication systems need to have a clear view of the sky. So you need more than one, so that, whatever course you're on, you don't have obstructions. Finding all that real estate and deciding what you're going to design around, given the fact that all those things are changing rapidly, leads us to the recommendation that we basically use a process of defining space, weight, power, cooling, and location in the design, so that eventually whatever the system we actually use has a place and has power and can be connected. We have a whole lot of acoustic systems, bottom mapping, profiling the water column, looking at the biodiversity. We have sonars that look forward. We have the ability to measure the currents and, a lot of things that was talked about earlier. In the lab spaces, there's computer control systems, displays, the whole server room to collect, process, or archive the data. All these things fit into our network diagrams. So sort of as a first step in cybersecurity, we've defined 3 different networks. We have the vessel network that has all the vessel systems. We have a guest network for the iPhones and the iPads, and we have a science network. And then there's interconnections between them. A lot of the science data goes into the ship systems for the bridge people to see. and vice versa. Navigation and all those things have to come into the science network. So I'm not going to spend a lot of time. You can look at these and they're evolving, but these are the first steps in sort of defining all the systems and equipment that needs to be connected and how they're connected. The same thing with the science network. And then within the science network, we have subsystems for controlling all the acoustics or for the MET sensors and then tying those all together and then putting them into displays and control systems. And of course, then the guest network allows people to get connected and get themselves onto the science network as needed. So there's firewalls between all those things. And so at this stage, like I say, we just sort of outline what we need. And we have in the next stages, we start to identify maybe more specific equipment. You know, the acoustic systems right now, there's not a lot of providers that do the things we want. So we have nominally identified, you know, specific acoustic systems. When we go back to the timeline, this ship won't actually start construction until 2027. It'll go in the water about 2029, delivered in 2030, ready for operations in 2031. Well, guess what? Things are going to change between now and then. So we want to make sure that it all fits. This is a diagram of how the cabling on, this is an Australian research ship, but if you've been on the Sally Ride or the Neil Armstrong or any of the others, they did a really nice job of running all the cables, all the science network cabling and the instrumentation, cabling. You have to be careful about not crossing that with or putting that right alongside major power cables. You have to worry about sort of interferences on your data. And so finding a place for all those things used to be just left to the people who are doing the installation. You know, this is generally, you're going to put it here. Now we're, you know, the practice is going into modeling things down to very small cables and pieces of equipment where they go, and identifying every single piece of equipment where it's going to go before you actually start construction. You got to make sure that you actually identified all the related equipment. On not Armstrong and Ride, we had a whole lot of stuff that had to do with the propulsion control system and the automation system, and we didn't have a place with the cabinets. We ended up putting them in the science hold and then having to build a cage because it needed to be secure. So these things had to be thought about ahead of time. Specifying, you know, the next phase, we start to specify equipment, but for the most part, that's going to wait till we actually start construction. We get closer to delivering the vessel, that, you know, the actual switches or routers or, you know, Wi-Fi systems, all that stuff. You know, we know where it's going to go. You know, what we actually buy is going to wait. And visualizing and diagramming all those connections is very important. I got 2 more minutes, so I got to keep going. So we've engaged we've got a science advisory committee that provides us a lot of input on what's needed from the science point of view, including operators and technicians that have done this work before. The academic research fleet has a cyber working group that meets weekly. Some of the people in here, I think Sean and some others, who participate in that. And so that's a very good resource for the people who are doing the design on this ship. I mentioned earlier, Samos and UDAS, those people are the rolling deck to RTR. They are all part of our experts that we go to. The Trusted CI and Compass CI have been helping us with looking at our plans. I've got a report from the Compass CI folks, and essentially they said, in a nutshell, take a look at what you're going to be doing and what's the daily need in terms of the data that you're going to collect, what you're going to do with the data, how it's archived, how you're going to use it. So we did a similar thing in terms of coming up with our endurance, 90 days. What are we going to do? So we had we put together a design reference mission. every day, what are we doing? Where are we going? How far do we go? How much fuel we burn? So we want to do something similar with the cyber infrastructure and cybersecurity. And so the next steps is to, go into the final design, finish up the network diagrams, start maybe being a little more specific about equipment, designing so that you support cybersecurity is an important part of what we'll be looking at. Continue to reach out to the science community, to the cyber community, the collaboration from people like you and the experts in the field is very important to getting this right. Construction stage, we got to find somebody to build the ship and get specific vendors and equipment and have them start being involved in the project. And finally do all the testing, trials and testing of all the equipment. Again, that's a good resource for seeing the reports and leading to the design of the ship and the current design. Something that we've been working on for many years. And we hope we have this kind of a ship to support Antarctic science for 40 years. Questions? My timer just went off, so I think I get it.